So good afternoon, everyone. I'm Shengkai from Shanghai Jiao University. It's a great pleasure to be here today to introduce our work on container networking ONCache to you all. This is a collaborative work between Shanghai Jiao University and Broadcom. Containers are widely used to deploy distributed applications such as MySQL, Nginx, Redis, and Spark. To support these distributed applications, container networks are crucial to connect containers to the underlying physical networks. We will start by revisiting current container networks. Existing solutions fail to provide high performance, low overhead, high flexibility, and good compatibility at the same time. So let's begin with the simplest types of container networks. In host networks, containers directly use the host NIC, which requires containers on the same host to coordinate ports with each other, and thus it limits application-side flexibility. And bridge networks and device virtualization techniques, such as MAC VLAN, IP VLAN, assign each container a unique IP and directly forward the packet to the physical network. However, these networks rely on the physical network to route the container IPs, and which adds network configuration requirements. In conclusion, these networks tightly couple containers and physical networks, resulting in limited flexibility on either side. To improve flexibility, overlay networks are a popular choice. Compared to bridge networks, they use tunnels, such as VXLAN tunnels, to transmit container packets. These tunnels encapsulate packets with outer headers, and then the packet could be routed in physical network by the host IP. In this way, containers are decoupled from the physical networks, offering much greater flexibility. However, this comes at the cost of reduced performance and increased CPU overhead. In our macro benchmarks, we observed a 29% drop in 1 byte request and response transaction rate, and a 45% increase in per byte CPU overhead compared to bare metal. To eliminate the overlay network overhead, prior work like SLIM introduced a socket replacement mechanism, allowing containers to use sockets established on the host NIC, thereby avoiding overlay network overhead. However, they have poor compatibility for connectionless protocols like UDP and SMP, limited by their socket-based design. So our paper also analyzes other types of networks. All existing container networks are not perfect. They fail to offer low overhead, high performance, high flexibility, and high compatibility at the same time, which motivates this work. So we now introduce ONCache, our proposed solution built on top of overlay networks. Overlay networks offer good flexibility and compatibility, but the challenge, however, is how to eliminate their overhead without losing the benefits of flexibility and compatibility. So let's first dive into the overhead introduced by overlay networks. We quantitatively analyzed the network stack of N-tier, SLIM, and bare metal. The additional overhead of N-tier and SLIM compared to bare metal is highlighted in the red font. Despite there are some differences between N-tier and SLIM, overlay network processing consumes near half of the CPU time on both the egress path and the ingress path. And within this overhead, connection tracking and packet filtering contributes the most to CPU usage. Thus, how can we eliminate this overhead without losing any functionalities? Remember, we still aim to preserve the flexibility and the compatibility of the overlay network. Let's briefly review how a typical overlay network handles container packets. So on the egress path, the process is as follows. First, packet filters verify whether a packet is allowed according to network policies, typically based on the packet's FIB tuple. And if the destination IP is on a remote host, then the bridge routes the packet to the VXLAN tunnel. And finally, the tunnel encapsulates the packet based on its destination and other tunnel configurations. And on the ingress path, a similar process occurs. The tunnel first decapsulates the packet after verifying the destination IP is on its local host. And the packet then undergoes packet filtering based on its FIB tuple and intra-host routing according to its destination IP. And finally, the packet is delivered to the target container. An interesting observation is for intra-host routing and tunnel encapsulation and decapsulation, the processing depends mainly on the destination IP. Thus, packets with the same destination IP get almost the same processing results. And similarly, packet filtering decisions are made based on the FIB tuple of a flow, meaning that the flow belonging to the packets belonging to the same flow will have the same filtering results. So we can conclude that overlay network processing acts with an invariance property on the FIB tuple level, that is the flow level. So this invariance property inspires a key insight, is that we can introduce caches to store the invariant processing results for each flow, thereby avoiding repetitive overlay network processing. So this is the core idea of ONCache. And when the first packet of a flow is sent, a cache miss occurs. And when the packet should traverse the original overlay network. And after overlay network processing, leveraging the invariance property, we could store the intra-host routing results, the tunnel outer headers, the packet filtering results in the local cache. And when subsequent packets arrive, as we have already cached their processing results, we can simply query the cache, applying the filtering routing results, and prepending their outer headers to the packet or strip them on the ingress path. And some files, such as the checksum of outer headers, could vary between packets, and these files need to be handled separately. And then the question is, how can we implement this design within the network stack? We know that container overlay network stack executes within the Linux kernel. However, directly modifying the kernel code is time-consuming and often inaccessible in many production environments. And fortunately, eBPF technology provides a way to safely run user-defined programs in the kernel at runtime, making it a suitable place to implement ONCache. Specifically, we use eBPF maps, which is like in-kernel eBPF storage as caches. And to initialize the cache, we hook two eBPF programs at the point where the egress and the ingress paths complete their processing. And these programs are responsible for initializing the cache with processing results of the first packet. Additionally, we hook two more eBPF programs at the start point of the egress and ingress paths of the overlay network. And these programs query the eBPF map for cached results, finish outer header prepending, routing, and filtering, and invoke the eBPF redirect function to bypass the original overlay network stack. And then let's quickly go through some design details. And first, many real-world filters are stateful filters. They match not only on the FIB tuple of a packet, but also the connection state. Fortunately, connection state also has an invariance property. That is, once the flow enters the established state, it remains unchanged until the flow terminates. So to leverage this, ONCache only initializes caches for flows that are in the established state. And second, network configurations, such as packet filters, can change at runtime. To ensure cache coherency, ONCache adopts such a four-step methods in the user space daemon to handle network changes. And first, the daemon pauses the cache initialization, and then it evicts the related cache entries, and then the affected flow will be processed by the original overlay network. And then the daemon applies the configuration changes to the original container networks. And finally, after the changes are applied to the original overlay network, we can resume the cache initialization. This process actually reinitializes the caches for the affected flows and therefore ensures the cache coherency. And finally, ONCache is compatible with many CNS such as Flannel and Trier, many links acceleration techniques, and switch mesh sidecars. And for more details, please refer to our paper. And then let's move on to the evaluation part. First, the quantitative analysis shows that compared to Trier, an overlay network baseline that use OVS in their network stack, ONCache effectively replaces the overhead of OpenWay switch and VXLAN network stack with a much more lightweight eBPF overhead, which mainly consists of cache query and header modification overhead. And in this way, ONCache significantly reduces CPU overhead on both the egress path and the ingress path. And next, let's look at some testbed results. For TCP 1-byte request and response transaction rates, ONCache improves single flow throughput by 36% and reduces per byte CPU utilization by 26% compared to Trier. And we also evaluate the performance in multi-flow scenarios, and there is also significant improvement. And as shown here, ONCache achieves performance close to that of bare metal. And for UDP 1-byte request and response transaction rates, ONCache has similar improvements. 34% for single flow transaction rate increment and 27% for CPU utilization decrease. And for multi-flow experiments, the improvement is also significant. And for UDP, we also achieved performance close to that of bare metal. And in contrast, Slim has poor support for UDP. And for connection setup performance, since ONCache simply falls back to the original overlay network for cache initialization, it does not introduce any additional overhead in the connection setup phase. In contrast, Slim requires an extra service discovery process, which significantly prolongs its connection setup time. And as a result, the connection creation rate of ONCache is more than 3 times higher than that of Slim, as shown in the figure. And finally, our evaluation shows that ONCache benefits real-world applications in terms of latency, transaction rate, and CPU utilization. We have evaluated on popular applications, including Memcached, PostgreSQL, and Nginx. And you can find more evaluation results in our paper. So, in conclusion, ONCache brings cache to the container overlay networks. It significantly reduces overlay network overhead while maintaining its flexibility and compatibility. We adopt an eBPF-based design, and therefore ONCache is easy to deploy to current clusters. We have open-sourced ONCache and welcome issues and pull requests. There are already companies that have tried ONCache and found improvements in their production environments. And I hope more researchers and developers would try it out and contribute to ONCache in the future. And that's all. Thank you for listening.